Hello everyone that's viewing this. Today we're going to be presenting our design project for our flight arrow. We're the team WinterSoldiers. We'll be presenting our design concept, the WS-1 Titan, to fit the next generation military transport aircraft design project. And here's a nice side view of our design concept, the WS-1 Titan. You can see that it looks pretty similar to the C5, and we're going to explain that as we go. And our next views show a nice front view and a top view. Alright, and we're going to go through our team structure and introduction. I'm Sean Parsons, and I'm the team lead, and I've been helping out in the CAD group and structures as well.
I'm Zayd Nabilsi. I'm the chief configurator, and I also work on the power and propulsion team.
I'm Jalen Golfin, and I'm team's capture manager.
I'm David, and I am the aerodynamics and controls team lead.
I'm Travis Estes, and I'm the team lead for power and propulsion.
I'm Matthew Pottinger, and I'm the team lead for the structures group.
And I'm Kayvon. I'm the team lead for systems and support.
Okay, so for our project, we were given a list of mission requirements, just to name a few. The biggest one is that we have to have a 6,300 nautical mile unfueled range, carrying a wartime payload of 120,000 pounds. Also, we need to cruise at a minimum Mach of 0.6. We need to have a maximum payload of 300,000 pounds. One more of cargo. We have to carry 44 463L master pallets or one M104 Wolverine assault bridge. For our market analysis, one thing that the military is focusing on is decreasing their overall spending. The two ways they want to do that are through reducing the maintenance costs for their aircraft and also reducing the fuel consumption costs for their aircraft. And we aim to do both of those with our new design. A couple of graphs here. The one on the left is showing you how much money that our military spends in relation to the rest of our federal government. On the right is a graph showing the spending of the U.S. military as compared to those from other countries. Here is a chart showing the maintenance cost that is allotted for aircraft by the U.S. military. If you'll notice, within that red box there, it's showing the price per year. There is a downward trend in that it started around $5.4 billion a few years ago. It's down to $4.6 billion roughly, and that trend will continue. So we aim to make our maintenance costs minimal. Here is a graph showing on the left the price of jet fuel as compared to the price of crude oil. As you can see, it's slightly higher. It went through a pretty big spike in the past few years, and it is likely to stay there. So we're going to reduce our fuel costs. The chart on the right is showing how much money the federal government spends on fuel for aircraft each year. In the box there on the bottom, it shows that there has been a trend in spending more money on fuel recently. It's around $18 billion now, and we aim to reduce that.
Okay, and we think it's also important to consider current capabilities and competitors in addition to the current market needs. So we're going to look at 3 aircraft that we consider to be fundamental as part of our fleet of transport aircraft. So let's start with the C-130. You can see that it's the most commonly used currently in the fleet. They've got 2,300 plus units. It's well known, it's familiar. But it was introduced in the 1950s, so you have to consider that it has higher repair and maintenance costs as well as having higher fuel efficiencies with 50 plus years of technology to make up. Another aircraft not pictured is the C-17, which it was introduced in the 1990s, so it's the most recent. However, it came in under budget and it didn't meet the design requirements, so it's not a good consideration to depart from. But we have the C5, which we consider most close to our design objective, with a payload of the biggest payload currently available at 250,000 pounds. It's relatively new compared to the C-130 coming in at the 1970s, but it's notorious for high repair and maintenance costs as well as not being fuel efficient. So in our point of departure, we're going to explain why we're choosing this as our point of departure, and we think there's a place in the marketplace for something familiar, but Travis is going to explain how we're going to make it competitive.
For our point of departure, we have decided to take the C5 and make what we feel to be the necessary changes to meet our objective requirements. This includes increasing the aspect ratio, which will be done by decreasing the root chord while keeping the same wingspan. We will also use the latest in engine technology. We will use 30 to 40% composite in our structure. We'll also improve the cockpit layout as well as the avionics using a modern fly-by-wire control system.
For aerodynamics, we ran an analysis on several different airfoils. One that particularly stood out was the MAE3253. The only problem is that it was pretty thin at 6% thickness, and so we decided to modify it and increase the thickness, increase a little bit of camber at about 3%, and we ran the analysis compared to a couple different airfoils, including the C5 and the purple. Ours is the analysis on top, and we significantly improved the CL max. And so from there, with that airfoil chosen, we ran a 3D analysis to figure out our plan form and our aspect ratio. And that ended up being at an aspect ratio of 9. It gave us a wing loading of 154 pounds per square foot and 76,000 pounds of drag. Next. Due to mission requirements, we were required to take off within 9,000 feet. So to accomplish this, we added things such as slats and flaps, and this effectively increased our CL max and our stall angle of attack, and this helped us take off in that required length.
For power and propulsion, we have decided to go with the GE9X engine. This is due to the fact that it has such a low SFC when compared to the engines that were previously used on the C5. This would be the GE-CF6 at a SFC of 0.33, as well as the GE90 at an SFC of 0.324. Also, GE estimates that their engine will get a 15% less fuel burn compared to the best engines currently available on the market. These engines will also produce 100,000 pounds of thrust each. This will allow us to use fewer engines, reducing our weight. Also, the increased reliability with these engines will help out with our aircraft. The entry to service for these engines is 2020, so they'll be plenty ready in time for our aircraft.
Okay, with the structures and material selection, we have a combination of traditional and composites. With the composites, it does reduce the weight and also make it stronger for a higher wing loading. But with the traditional, it is easier to manufacture and it's easier to maintain. When we're putting this on our aircraft, we're going the composites will be on the fuselage skin, and the traditional materials will be on the inside with the ribs. And with the wing structure and the empennage, we'll be having mainly composites with a overlapping to help with maintenance, and instead of having a all-one composite. And this is what our structure of our Titan will look like. It's going to be similar to the C5, where it's going to have a pressurized cockpit and troops in the top above the cargo area.
Okay, so for systems avionics, we've implemented a state-of-the-art glass cockpit. This uses heads-up display, which provides primary flight information to the pilots during critical flight conditions. In addition to this, we have our flight management system and enhanced vision system. This uses infrared technology and sensors to provide a picture to the pilots on the heads-up display for low visual flight conditions. In addition to this, we're using helmet-mounted displays, and we're using this with 360 infrared cameras, provides an all-around view to the pilot. In addition, we're using a fly-by-wire system, and not only does this make the aircraft lighter, but it allows us to use flight envelope protection, and this helps prevent the aircraft from stalling during critical flight maneuvers. So here on the left we have our component layout. We have our cockpit command station, second level troop seating and our C5 inspired cargo bay. And on the left we have, or right we have a cross section of our aircraft. Current C5 holds 32 pallets in 2 rows. Our aircraft holds 44 pallets by including a rack and roll system near the front of the fuselage above the 4 pallets. Not only does this allow for easy unloading, but also for easy loading as well.
As far as performance we can expect with the WS-1, the range with a wartime payload we can expect is around 6,700 nautical miles, and that's with a payload of 120,000 pounds. And our aircraft should have a max payload of right around 300,000 pounds. It will cruise at a Mach of 0.7, and it'll have a takeoff distance of 6,700 feet. It'll have a time to cruise altitude of right around 18 minutes, and it'll have a max speed of Mach 0.8. Our aircraft will also have a gross takeoff weight of right around 912,000 pounds. As far as fuel consumption, we expect our aircraft to require right around 350,000 pounds of fuel for maximum range, which is approximately 51,000 US gallons.
Okay, and we're going to sum up our design presentation by comparing our design features with our point of departure features. So let's start with looking at our maximum payload. We've increased it from 250,000 pounds to 300,000 pounds, which will be the largest carrying capacity in the fleet if implemented. We have increased our gross takeoff weight from 840,000 to 912,000 pounds, which we consider acceptable. Our range is a dramatic increase from 2,400 nautical miles to 5,700, so more than double improvement there. Our fuel capacity originally was only 51,000 gallons, but the one on our design is going to come around 60,000 gallons. And our next one is what we believe is going to make us competitive in the marketplace. If you took the existing C5 and flew 6,300 nautical miles, it would take you 55,000 US gallons. But for our design, it would only take you about 43,000. So if you multiply that times the price of today's jet fuel, in that one trip alone, you would save $18,000, which we consider a definite success for this design concept. Our rate of incline is also improving from 1,800 to 2,100. With composites, we are able to increase the wing loading from about 120 to 154. Our aspect ratio, as previously discussed, is increasing from 8 to 9. And another big improvement we're very proud of is our thrust to weight ratio is doubling from 0.22 to 0.44. Our cruise Mach is a little less, coming in at 0.7 compared to 0.77, and our maximum speeds remain about the same. So in conclusion, we feel we've done a good job of taking our point of departure and producing something with better results, better fuel efficiency, lower repair and maintenance, and a higher cargo carrying capacity. So, thank you for watching our design presentation. $123.
No.